All right, well, let's get to chapter 5, everybody. So I guess I should pull up my slides. Yeah, here we go. So this is chapter 5, a brand new chapter which deals with the topic of stereoisomerism. So stereoisomerism, and this is a chapter that you might find handy to have molecular models. Might be handy to have a molecular model kit to do this chapter. Not necessary, but it might be handy. Anyhow, let's do a little review here of what isomers are. And isomers are just compounds that have the same molecular formula. There's two types of isomers, constitutional isomers and stereoisomers. Constitutional isomers you're already familiar with. These are compounds that have the same molecular formula. Like, for example, let's say we have something like C2H6O. There's two ways to connect that. We could either make ethanol, which is CH3CH2OH, or we could make dimethyl ether, which is CH3OCH3. These are two very different compounds with different boiling points, different melting points, etc., but they have the same molecular formulas. It's just the way that the atoms that are connected together that makes them different molecules. The other possibility is what we call stereoisomers. It says same molecular formula and same constitution, but different spatial arrangement of atoms. So the key word here is going to be spatial. The atoms are oriented differently in space somehow. And I'm going to give you some examples of that. Let me just give you one right now. Let me go back to my video here. So just bear with me. If we go here. Okay, so what I'm going to show you right now are two models that I've made. So if you look at these two models, they each consist of a black in the center. We'll call that carbon maybe. And then they're each attached to a red atom, a yellow atom, a blue atom, and a white atom. And my question to you is, these atoms have the same connectivity, right? But are they the same molecule? Could anybody answer that? Are these the same molecule, yes or no? No, they're not the same molecule, are they, Sean, right? Because no matter how I try to overlap them, I'll always be able to get two of the atoms to overlap, like the white and the yellow are here, but the green and the red and the blue won't. And if you're sitting there thinking, well, you're not holding it the right way, Mr. Dion, yes, I am, because it doesn't matter what you do. If I overlap the green and the blue, now you can see that the white and the yellow or the green, they're not matching. So these two molecules have the same constitution. They're both a black connected to a green, a red, a blue, and a white, but they are not identical molecules. And so that's something that we want to keep in our mind as we move forward. So we can have the same connectivity, but we have a different arrangement of those atoms in space, and so they are not identical. All right, and that's what we call stereoisomers. Now, what I just showed you is one type of stereoisomer. Those are called enantiomers. They're non-superimposable mirror images, and we're going to get to that in a little bit. So one form of stereoisomerism that you've already seen in this class would be cis and trans. If you look at these two molecules here, cis 1,2-dimethyl cyclohexane and trans 1,2-dimethyl cyclohexane, what do they have in common? They both have a cyclohexane ring with two methyl groups on it. Okay, so they have the same connectivity. They're just a 6-membered ring with two methyl groups. How are they different? Well, on one of them, you have the two methyl groups on the same side. That's the cis molecule. And on the other molecule, you have one up and one down. And that's the trans molecule. But again, these two compounds have the same connectivity. They have the same connectivity. What differs? The difference is the orientation of the groups in space. And so we say that these two compounds are stereoisomers. So cis-trans isomerism is one form of stereoisomerism. Now, not only did we see cis and trans in a ring, we also saw cis and trans in a double bond. Let's say I have this compound here. This is cis-2-butene, and this is trans-2-butene. Just to review, Cis is when you have two groups on the same side of the ring, or sorry, the same side of the double bond. And trans is when we have two groups that are on opposite sides of the double bond. Both of these compounds have the exact same connectivity. They're both a CH3 attached to a CH with a double bond and a CH and then another CH3. What differentiates these two molecules? It's the relationship of the atoms in space with each other. And so again, cis-trans on a double bond is another form of stereoisomerism. So to review, what are the two forms of stereoisomers that we've seen so far? Cis and trans on a ring, and cis and trans on a double bond. Both same connectivity, but different arrangement of the atoms in space, and therefore they are stereoisomers. So what we're going to do next class is we're going to come back on Thursday and we're going to cover this problem. We're going to go over these 5 pairs of compounds and we're going to determine whether they're constitutional isomers, stereoisomers, or if they're just the same compound. All right, we'll take a look at that on Thursday. The same thing with this question here. It's identifying compounds as cis, trans, or neither. We're going to take a look at this on Thursday. So going back to this whole idea of cis, trans, stereoisomerism, that's only one type of stereoisomeric relationship. There are several others. And it says that to identify stereoisomers, we must be able to identify what's called a chiral molecule. And a chiral molecule, or sorry, a chiral object is one that is asymmetric. And all that means is that it's not going to be superimposable on its mirror image. You can test whether two objects are identical by seeing whether they are superimposable or not. So you can see that if I took this pair of John Lennon glasses, or whatever you want to call them here, they have the two purple lenses. If I look at the mirror image, I could put the mirror image on top of the original image and they would overlap perfectly fine. And so the glasses that have the two purple lenses, it's not a chiral object because it's superimposable on its mirror image. But if I took the pair of glasses that's shown in the mirror here, and if I redrew those, so if I redrew them, one like this and one like this, and then I just kind of connected them like this, now I'm going to have the purple lens. So where's my purple? I'm going to have the purple lens on this side, and I'm going to have the white lens on the other side. And you see that if I take this pair of glasses, they do not overlap with the other pair of glasses. You can see that they do not overlap. And so the pair of glasses with one of the lenses knocked out, that would be considered to be a chiral object because it's non-superimposable on its mirror image. Give me a thumbs up if you follow me on that. Chiral means it's non-superimposable on its mirror image. Okay, cool. Well, then if you understand that, let's move on and talk about why chirality is important in molecules. The reason it's important in molecules is if you have two molecules that are chiral, so mirror images that are non-superimposable upon each other, their connectivity is the same. They're going to have the same melting point, same boiling point, and all that kind of stuff. The only thing that's different is the orientation or the arrangement of the atoms in space. But what's interesting is that the receptors in our cells are also chiral. And so just because two molecules have the same connectivity, if they're not identical, meaning if they're stereoisomers, their pharmacology can be drastically different. You might have a drug that has some kind of desired therapeutic effect, maybe it fights cancer, but if you take its non-superimposable mirror image, which is known as the enantiomer, and we'll get there in a second, you could take its non-superimposable mirror image, and that might be a mutagen, for example, or it might, cause a person to go into cardiac arrest. Who knows? And so this is why molecular chirality is so important for organic chemists. Now, visualizing compounds in 3 dimensions can be very tricky for some people. For others, it comes more naturally. And so that's why it might be a good idea for you to use handheld models in this section. You can buy a model kit from Jeff Bezos at Amazon for not a lot of money, and I would recommend doing that if you're struggling with manipulating shapes and molecules in your mind. So this is the example that I just projected on the screen to you a few minutes ago. I had these two molecules. I had a black atom in the black atom in the center. Then it was connected to a red, a white, a blue, and a green. And you can see that these two molecules do not overlap with each other. If you don't believe me, I could prove it by redrawing the molecule if I could do it, and I'm not that much of an artist, but I'll try my best here. So if we do something like this, we'll shade this one in red, this one in green, and then this one in blue like this. So if I take this compound and I try to overlap it here, you can see it does not overlap, right? It does not overlap. You can see that the red and the green overlap, but the blue and the white do not overlap. And so these two molecules are non-superimposable mirror images. They're very different molecules. And again, if you need to make a model to prove that to yourself, I would highly recommend doing that. So what do you notice about these molecules? Okay, these molecules here that we call chiral molecules. You'll notice that they each have a carbon in them that is attached to 4 different groups. You notice that this carbon on the left, I'll put a little star by it maybe, okay? It's attached to 4 different groups. It's attached to a hydroxyl, a proton, an ethyl group, and a methyl group. Notice I didn't say 4 different atoms. I said 4 different groups. We can see some other examples of that over here. When carbon forms a tetrahedral center with 4 different groups attached to it, not necessarily atoms, we call that a chiral center or a chirality center or a stereogenic center or a stereocenter. They all mean the exact same thing. If you look at each one of these carbons that I have highlighted in green, you can clearly see why they are chiral centers. This one on the far left, we're missing a hydrogen that's not drawn in the bond line structure. So that carbon highlighted in green is attached to the hydrogen, chlorine, methyl group, and ethyl group. Therefore, it's a chiral center. The one in the middle is a chiral center, and you can even try it with this one here. Okay, this carbon is attached to a hydrogen, a bromine. This is a CH, okay? And then this one here is a CH2. So clearly, those are 4 different groups. So that's how we identify a chirality center. Each highlighted carbon, if it's a chirality center, is bonded to 4 different what? Groups. And when a carbon is bound to 4 different groups, we call it a chirality center. And so what we're going to do next class is we're going to identify all the chirality centers in these molecules. So we're also going to take a look at vitamin D and see if we can identify all the chirality centers in that molecule. So I told you a couple of times, I've let this word slip out of my mouth, is that when you have 2 molecules that are non-superimposable mirror images, we call these enantiomers. Okay, 2 molecules that are non-superimposable mirror images. Your 2 hands, if you hold them up, they're mirror images of each other, but you can't put them on top of each other. You can't put your left hand in a right-handed glove, so your 2 hands would be considered to be enantiomers. Now, if you want to draw the mirror image of this compound here, how would you do that? How would you do it? You'd be very careful and you'd say, well, I'll just draw a bond like this and like this, and then put my wedge up here. And there you go. I've done it. I've drawn the mirror image. I don't think anybody would disagree with me that this is the mirror image, but there's a much easier way to do it. If you want to draw the enantiomer of a compound in a much easier way, which is going to be necessary when we have multiple stereocenters, all you have to do is redraw the compound, and anything that's a wedge, you turn it into a dash, and anything that's a dash, you turn it into a wedge. And so, yes, these 2 compounds are enantiomers, but these 2 compounds are enantiomers too, right? This compound and this compound are identical to each other. Give me a thumbs up if you see that. That those 2 compounds are identical to each other. Great. All right. And if you have to use models, again, I highly recommend doing it. So like I said, if you want to draw a pair of enantiomers, all you have to do is flip any dash to a wedge and any wedge to a dash. So we can clearly see why this is a pair of enantiomers. And we can clearly see why this is a pair of enantiomers. However, these 2 compounds here, these are not enantiomers. Why are they not enantiomers? The reason why they aren't is because this is not a chiral carbon, right? It's not a chiral carbon. That carbon is attached to a hydroxyl group, a proton, but then it's attached to 2 methyl groups, CH3, CH3. These are the same. And so it's not a chiral carbon, therefore it doesn't have a chiral center, therefore it doesn't have an enantiomer. And that brings us to the Kohn-Ingold-Krelog rules. I thought I was going to cover these today, but I'm going to save these for Thursday morning.